Hi there, welcome back. I'm so happy you're here. Before I jump straight into the problem that I have put together for you today, I want to show you a free guide that I prepared for you. It is called How to Evaluate Your Engineering Education in United States of America, and it does just that. Let me show you. This is the Education Evaluation Starter Guide. It has a welcoming page here, and then it starts right away with every step you need to do to evaluate your education. Create an account on ncs.org, step number 2, number 3, gives you 4, 5, so on, and then congratulations page, and the page where I'm showing you where you can find more training and videos on my YouTube channel, FE Made Easy, is where you're watching me right now. If you are interested in downloading this file for free, please click the link below underneath this video. Okay, another important thing that I want to remind you is that if you do like this video, please subscribe and give it a like, because this helps people like you find me. It's just the way YouTube works. It helps promulgate my video in front of more people. Now let's move on with our example. Draw the shear and bending moment diagrams for the beam shown below. The beam has an internal hinge at B, 6 feet from the left support. As you can notice, this is not a usual simply supported beam. This beam has a hinge in the middle. So in order to solve it, we're going to have to actually solve for this part first. Draw the shear moment diagram, and then take the reaction that we have here and add it as a load, and solve for this side. Draw the shear moment diagram, and at the end we can just combine and draw the total shear moment diagram for the entire beam. So let's do that. I'm going to take this side. And the reason we're taking this side is obviously because if I'm going to take this side, then we're not going to have a simply supported beam. We're going to have more unknowns. So this support has 3 unknowns. Here we have a horizontal load, which is obviously 0 because I'm going to add it anyway because we don't have any horizontal loads. So this reaction, horizontal reaction, is going to be 0. I'm going to call this A, B, C, and then we have a vertical reaction. I'm going to call it VA, and also this is going to be MA. So and this hinge has 2 reactions, horizontal and vertical. So if we are going to take this side, we're actually not going to be able to solve it. So that's why we're going to take first this side and then the other side. So let's start by calling it, or you know what, I'm gonna go lower because I want to draw at the end the shear moment diagram for the entire beam. So our beam looks something like this. Here we have a load, and here we have a roller, and this is going to be C. Reaction at C, this is reaction at B, and the horizontal reaction I will add it just because this support has a horizontal reaction, but in this case it's 0 because we don't have any horizontal loads. This is 4 and this is 4 feet, and the load over here is 5 kilonewtons per foot. Okay, so let's solve for the reaction. Let's do sum of moments in point B equals 0. We have reaction at C times 8, that rotates counterclockwise, minus 5 kilonewtons, 5 times 4, and the arm is 6, equals 0. From here, reaction at C equals 2, going to be divided 4. 5 times 4 times 6, it's 120. And the reaction at C equals to 15 kilonewtons. I'm going to add it here. 15. Okay, and then we can do either sum of forces in the y direction or sum of moments at C. I will do sum of forces in the y direction equals 0. Here we have VC plus VB minus 5 times 4, which is 20, equals 0. From here, VB equals to 20 minus VC, which is 15, and VB equals 5 kilonewtons. I will add it here. VB equals 5 kilonewtons. And now let's draw a shear moment diagram. So we have the shear here. We have positive at the top and negative at the bottom. We start at 0. So looking at the beam, I'm gonna go up 5 units. So this is going to be 5. And then on this section, I actually have to draw a line here as well. So on this section, I don't have any loads, so my diagram is going to be constant. Means I have here 5 as well. And now on this portion, let me put this positive. And now on this portion, I'm looking at this side and I'm going downwards with the value of 5 times 4, 20. So meaning I'm gonna be here, my value here is gonna be 15. So now we are here at 15. Here we have positive, here is negative, and from 15, looking here at the beam, I'm seeing that my reaction is 15, so I end up at 0, which is perfect. And now let's draw the moment diagram. And here, I'm going to do negative on the top and positive at the bottom. So now, in order for us to draw the moment diagram, we have to calculate the areas of the shear diagram. So here, we're going to have 4 times 5, this is 20. And notice how in this case, we actually need these distances in order to be able to calculate the areas. It's actually very simple to calculate these distances. We're going to use the similar triangle rule. And so I'm going to have this triangle over here, which is going to be similar to the big triangle. So the way I'm going to do this, I'm going to try and explain. So imagine that I'm going to slide this point all the way to 0, meaning in this side, it's going to go up 15 units as well. So this side is going to be 20. My small triangle, which is 5. And here I have X. And then I'm going to also have my big triangle. And in this, I'm going to have 20. And the total length here is 4. So we do 5 relates to X the same way as 20 relates to 4. And from here, X equals to 5 times 4, which is 20, 20 over 20, and X equal to 1. So here I have X1 and Y is going to be 3. So now we can calculate the area, and area for this triangle is going to be 5 times 1 divided by 2. It's going to be 2.5. And on this side, 3 times 15 divided by 2. We're going to have 22.5. All right. And now we're ready to draw the moment diagram. So when we have a pin support, we start at 0. And looking at the diagram, it is positive. So we're going to go towards the positive side with a value of 20. And my diagram is going to look linear because the shear diagram is constant. So I'm going to have 20 over here and starting from 0 going linearly. And this is positive. And again, if you are used to doing it positive on the top, negative at the bottom. Just please do it that way. It's really there's no difference. So let's continue now. Here, when a shear diagram intersects here like this, we actually have to draw a line down, because at this point we're going to have a maximum or a minimum. So let's see. We have 2.5 is positive, which means we're going to go towards the positive. And here it's a little trick that I have to show you. We have to know which way are we going to go. Are we going to go, of course it's going to be parabolic, but are we going to go this way, or are we going to go with our parabola this way? So let's see. Let me see. Somebody explained it this way online, and I thought it's a good way, and I remember it very well since. So I think I'm going to explain it the same way to you. So our triangle looks like this, meaning goes from a big value to a smaller value, right? So imagine now, think about a ski slope, and think about how you're going to go fast and then slow, right? So I'm going to go fast and then slow. And imagine if our triangle was going to look different. I'm going to go, it goes from a smaller value to a bigger value. And if we think at the ski slope, we're going to go slow and then fast. So it would be slow and then fast, right? So this is the easy explanation that I found online, and that I thought it's very useful. So in our case, we are going to, our diagram is going to look, it's going to go fast and then slow, which means it's going to look like this. So I'm going to go fast and then slow, and it doesn't look very good, but the point is that this value now, it's going to be 22.5, and this is positive. And now on this portion, I have to go towards the negative side, and I have to go the value of 22.5, which is great. This is a way for you to verify yourself, because you have to end up at 0. And I'm going to go slow and then fast, because my triangle goes from a small value to a bigger value. So I'm going to go slow and then fast. So this looks much better. And this is still positive. And there you go. We're done with the first side of the beam. And let's go and do the other side. Beam looks like this. And now let's pay attention to the little hinge over here, to the reaction. So my reaction over here, I got 15. Oh, excuse me, I had 5, right? Because the hinge is over here on this end. So I had 5, and the reaction goes upward, meaning the reaction on the beam, it's actually going to go downward. So I'm going to add the 5 kilonewton reaction here. And then I have over there a moment, 50 kilonewton moment, and a force going downwards, 20 kip force. No, I just realized that this is actually not kilonewtons per feet, it's kip per feet, because it doesn't make any sense, correct? Like, what have I done here? So this is actually kips, and this is actually kips, and kips. I will go ahead and just take it away from here. I hope it didn't confuse you, and if you caught that, good for you. Okay, so I have a 20, a 50 kip load moment, kip foot, and this is 5 kips. Okay, and in here, I'm gonna add my reaction, VA, that we have to calculate. I will add the moment, MA, we have to calculate as well. And I will also add the horizontal reaction, which is HA, and I will add it as equal to 0 because we don't have any horizontal loads. So let's go ahead and do this side of the beam. And first, I will also add the dimension here. Okay, we have 2 feet, 2 feet, 2 feet, 2 feet. So it's 2, 2, 2. So we start by doing the sum of moment in point A equals 0. Results, we have MA minus 20 kips times 2 minus 50 kips minus 5 kips times 6 equals 0. From here, MA equals to 40 plus 50 plus 30, and it results that MA equals to 120 kip-foot. All right, and now for the reaction, we're going to do sum of forces in the y direction equals 0. And here we have VA equals, or let's do VA minus 20 minus 5 equals 0. Results, VA equals to 25 kips. So this is 25 and MA equals to 120. And now let's draw the shear moment diagram. We have shear and we have moment here, positive, negative. Okay, let's start with the shear. We start at 0 and have to go up 25, and of course I forgot to draw this. Draw the lines down because each sector has a different. So I'm going 25 up, and looking at the beam, my diagram is going to look constant because we don't have anything happening on the beam. And now getting here, I have to go 20 kips down, meaning this value here is going to be 5. And again, I have to, my diagram is going to be constant. Nothing is happening on the beam. And here, still 5. I don't have any loads. So the next section is still going to be 5. It's constant. And I'm getting at this point and going downwards, the value of 5, which makes me end up at 0, which is perfect. This is a way for you to verify yourself if you drew the diagram correctly. You have to end up at 0. Now let's calculate the areas so we are able to draw the bending moment diagram. This is 25 times 2, 50. This is going to be 10. And here I'm going to have 10. All right. So when you have a cantilevered beam like this, for the moment to be positive, it's got to be clockwise when you come from this direction. So in my case, the moment go is counterclockwise, which means it's going to be negative. So I have to draw my moment on the negative side. So the moment is 120. So I'm going to draw 120 here. This is going to be 120. And then the diagram is going to look linear because the shear is constant. And I'm going to go towards the positive side because the shear diagram is positive with the value of 50, which means I'm going to end up here at, this is going to be 70. It's going to be linear. Okay. So now from 70, the next section is going to be linear as well, and I have to go lower with 10, and it's going to be linear. I'm just going to go to here, and this is going to be 60. And now let's see what's happening here. Every time you have a concentrated load, it creates a jump in the shear diagram, like here. See, it doesn't continue from here. We had a jump. And every time you have a moment on the beam, it's going to create a jump on the beam diagram, on the bending moment diagram. So here from 60, and this is very important because this is very easily to, it's very easy to make a mistake. So from 60, look at the beam. We have 50 kips, and we're coming from the left side. The moment goes clockwise, which means the moment we're going to go towards positive. So 60 going towards the positive with 50, I'm going to end up at a value of 10 here. So now from 10, I have to go downwards towards the positive, again linearly, and I'm going to end up at 0, which is great. And I forgot to add, everything here is negative. Everything is negative. Okay. And this is negative as well. Let's go back and connect all our diagrams together. So here I am. And then this is going to be the shear diagram here. And I'll have positive on the top and negative at the bottom, and moment diagram. And I will draw the line. So VA was 20, is 20. Here VC was 15. So in here we went up with the value of 20, and then the diagram was constant. This is positive. And then we have to go downwards 20 kips, which means I'm going to be left with 5 kips here. And then moving forward, the diagram is going to look constant. Here we have 5 kips as well. Okay, moving forward, nothing is happening on this section, so the diagram is going to be constant. Okay, here we have 5 kips as well. And now from here, nothing is happening on this section either. Gonna go constant. Here we have 5 kips. And then here we have that linear diagram. And we have to go downwards 5 times 4, which means I'm going to end up here at 15. And I'm now on the negative side here. So let's show that. And here is the positive. Okay. And then the moment diagram, I will have negative here and positive on this side. I started with the moment, which is 120. And then I'm going downwards with 50, which leaves me here with 70. And this is negative. And then from 70, going down with 10. 5 times 2 is 10. So I'm going to go lower a little bit wavy, but that's okay. It's linear, just so you know. And again, on this side, we have the moment, so we have to go towards the positive with 50, which is we're gonna end up at 10. Going lower 50, meaning this value is gonna be 10. And from here, we're gonna go downwards linearly 5 times 2, 10. And we're gonna end up here at 0. So again, linear, negative. And then from 0, we have to go linearly towards the positive side with a value of 5 times 4, 20. So here we're gonna have 20. And now we are on the positive side. Here it is. And remember, when you have the shear diagram intersecting like this, we're gonna have a minimum or a maximum moment. So you have to draw a line here. And then this was 2.5, and it was going from big to small, which means if you think of a slope, you're gonna go fast and then slow. Again, this is not that great, but and then this value is going to be 22.5, and it is positive and it's parabolic. And from here to here, this word area is 22.5, and we're going to end up at 0. And again, maybe I should make it more parabolic. Again, positive. End up at 0. So the diagram for the entire beam, it's going to look like this. You can even write it down. It's parabolic. And this is its linear, just to let your teacher know that you actually know what you're doing here, in case it's hard to say. Okay. And that was it for today.